Assalamualaikum and greetings everyone. Today's topic is on local extrema, which is the last application of partial derivative that we're going to cover in this course. Okay, extrema here refers to either maximum or minimum. Okay, now let's look at definition 2.5. Suppose z equals f of xy is a function of two variables defined in a domain D and that AB is in domain D. Okay, here we have two items. The first item, FAB is a local maximum of the function f if there exists region R, which is a subset of D, such that AB is in R and f at AB is larger than or equal to fxy for every xy in R. Okay, let's see here. So here, let's say we have a domain D. Okay, so let's say this is domain D. And in domain D, we have region R, which is a subset of D. And in domain, in R, we have a point AB. And it says here, FAB is a local maximum if AB is in R is in D, and f at AB is the largest compared to the value of f at any point xy in region R. So when we compare the value of f at any point xy in region R, f at AB is the largest. Then f at AB is called the local maximum. Okay, so it's not the largest in the whole domain, but it is the largest in region R, where R is inside the whole domain. Okay. The opposite of that is item 2. FAB is a local minimum of the function if there exists region R, which is a subset of D, the domain D, such that AB is in region R and FAB is less than or equal to fxy for every xy in R. So this is the opposite of what we had in item 1. So here AB is in region R, but the value of f at point AB is the least compared to the value of f at any other point in R. So that makes FAB a local minimum because it's the lowest value compared to other value of f at any other point xy in region R. Okay, all right, so that is definition of local maximum and local minimum. Now let's look at theorem 2.6. Here, suppose we have FAB is either a local maximum or a local minimum, and the derivative of f exists, partial derivative of f exists at point AB. Then partial f partial x at point AB is 0, and partial f partial y at point AB is also 0. So if FAB is local maximum or local minimum, then partial derivative of f at the point AB will be 0. Okay. Note here, there's a note. It says the reverse statement of the theorem is not necessarily true, meaning that if partial f partial x and partial f partial y are 0 at point AB, that does not mean f at AB is a local maximum or a local minimum. But if f at AB is a local maximum or local minimum, definitely the partial derivative of f at point AB will be 0. Okay, that is theorem 2.6. Okay, now I'm going to show you another theorem which is called second derivative test, where we can determine whether our critical point is maximum, minimum, local maximum, local minimum, a saddle point, or neither. Okay, this is what we call the second derivative test. We're going to use second derivative test. This is the theorem 2.7, so I'm not going to go over how to get the theorem. I'm just going to show you the theorem and we're going to use it. Okay, so first of all, this should be a point, not a pair. Okay, a point AB such that partial f partial x and partial f partial y at AB are 0 is called a critical point or stationary point. And in some books, they also use equilibrium point. Okay, but I'm going to use critical point because it's easier to say. Suppose fxy is a function of two variables that has continuous second partial derivative, meaning that we can differentiate f with respect to x and with respect to y twice. Okay, we can find fxx, fyy, and also fxy. And on a region R, and AB is a critical point in R, then, okay, we have four conditions. First of all, we have to find G at point AB. What is G? G is the determinant of a 2 times 2 matrix, where in the first row we have fxx, fxy. You can see those are all second partial derivative. And in the second row we have fyx, fyy. So when you take the determinant of this, what you have is fxx times fyy. Remember, a, b, c, d, the determinant. ad minus, okay, and then we have fxy times fyx. But from before, we know from Euler theorem, fxy is equal to fyx if the first order and the second partial derivatives are continuous. So from here, when this is equal, then fxy, fyx is really fxy squared. Okay, so that's how we get the this formula here. So you do need to remember this formula, because to determine whether it's local maximum, minimum, or saddle point, or neither, depends on G here. Okay, so we have 4 conditions. FAB is called a local maximum if G is positive and fxx is negative. Second, FAB is local minimum if G is positive and fxx is positive. And here we have a point A, B, that is x condition, x coordinate, B is y coordinate, and FAB is the z coordinate. So it is a saddle point if GAB is less than 0. So if it's less than 0, you don't have to check for fxx. Straight away you know that is a saddle point. And the fourth is when GAB is exactly 0. So if it is exactly 0, then no conclusion can be made, meaning that we cannot use the second derivative test. Okay? Alright, so you do need to remember this condition A, B, C, and D. Alright? Okay, now let's look at an example. Okay? Example says, find the critical points of the following functions and determine the nature of those points. So I'm gonna solve only one of them. Let's say that one. Okay. Fxy is equal to, okay, we're gonna solve that. What is this? Okay. Example. Okay, hang on. Let me split the view. Oops. Dear. All right. Example. Here we have a function z equals fxy is equal to 2y cubed minus 6xy minus x squared. Okay, we need to find critical point or points, because in some case we do have more than one critical point. Okay, so first we need to find critical point. So to find critical point, we have to solve for partial x equals 0 and partial f partial y equals 0. Okay, so we have to solve 2 equations simultaneously. Okay, let's find partial f partial x. We differentiate f here with respect to x by holding y as a constant. Okay, so that will give us, the first term will give us a 0. Second term will give us negative 6y. The third will give us negative 2x. And this must be equal to 0, because at the critical point, partial f partial x is 0. And then we need to find partial f partial y. That will give us 6y squared. Second term will give us negative 6x. The third will give us a 0. Okay. And then let's call this equation 1 and equation 2. Remember, because we need to solve the 2 equations simultaneously for x and y. Okay, some of you can do this very quickly, because we are here in the process of finding the critical point. Solve the 2 equations simultaneously. Okay, let's say we start with equation 1. We have this. Okay, so from equation 1, we can rewrite this as 2x equals negative 6y. Some of you can do this very quickly, I know. So here we get x is equal to 3y. I want to put a box around this. Okay, so this is what we obtained from equation 1. And now we're going to use that in equation 2. Into equation 2. Okay, so in equation 2, we have partial f partial y is equal to 6y squared minus 6x. So that x there will be replaced by negative 3y, which is what we obtained from solving equation 1. So from here we get 6y squared plus 18y equals 0. Okay, alright, so now from here we can find the value or the values of y by factoring 6y out. So you get 6 plus sorry, that's not 6. That should be y plus 3 equals 0. Alright, so from here we get two equations. We have 6y times y plus 3 equals 0. So it's either 6y is 0 or y plus 3 is 0. So from here we get y is 0, and the other we get y is negative 3. So from here you can see that we have two values of y, meaning that from there we can get the value of x. Alright, so at y equals 0, now we can use the equation that we got when we solved for equation 1. So from there we get x is negative 3 times 0, which is 0. So we have a critical point. So from here we get the critical point now would be x 0, y 0. Okay, now let's get another critical point when y is negative 3. So we get x equals, now again we replace y in negative 3 there. So we have negative 3 times negative 3, which give us a 9. So from here we get another critical point, which is x is 9, y is negative 3. So we have two critical points. So the critical points are 0, 0 and 9, negative 3. Okay, so now we're gonna we're gonna use second derivative test to check whether there are local maximum, local minimum, or neither. Okay, so to check for to use second derivative test, we need to find second partial derivative, which is fxx, fyy, and fxy, this one. Okay, right, so we need fxx. For fxx, we need to differentiate partial f partial x, which is this one, with respect to x again. Okay, so that will give us 0, 0, and that would be negative 2. Okay, and we also need fyy. Here we need fyy. So for fyy, we differentiate this partial f partial y with respect to y again. So that will give us negative 12y. And this term here will give you a 0. So we have negative 12y. And we also need fxy here. Okay. So for fxy, we start with partial f partial x again, this one. But we differentiate it with respect to y this time. So it's going to be negative 6. Okay, all right, so now we can get g. Remember g is fxx fyy minus fxy squared. Okay, so fxx is negative 2, fyy is negative 12y, and fyy you must be screaming there. Okay, fyy is not negative 12, it's going to be 12y. My mistake there. Okay, that should be positive 12y because we differentiate partial f partial y with with respect to y again. So that will give us 12y 0. Okay, my bad. Sorry about that. So that should be 12y. Okay, and minus fxy squared, that will be negative 6 squared. So here we have negative 24y minus 36. So this is our g at xy. Okay, so now we need to find g at those two critical points. So here we have two critical points. So usually if we have more than one critical point, I'm going to use a table. Okay, it's more systematic that way. So the table would have 4 columns. One is for the critical point, the other one is for g, and once we get g, we need to check for fxx because it can be positive or negative, so it can be local maximum or local minimum. And then the last bit would be the conclusion. Oops. Oh dear. Okay, sorry about that. Oh dear, what happened? Okay, all right. Okay, the first column is for critical point, so I'm going to call this AB, which is really the critical point. And next we need to find G, and if G is positive, we have to check for fxx, and then the conclusion. Okay, we have the first critical point is 0, 0. Okay, at point 0, 0, G is, okay, what is G at point 0, 0? This is G. This is our G. Okay, at point 0, 0, G is equal to 0 minus 36, which is equal to negative 36. So when G is negative, you don't have to check for fxx because this will fall straight into case C, which is a saddle point. So straight away you can get 0, 0, and f at 0, 0. F at 0, 0, what you do is you just go to f, which is this one. That would give you the z coordinate. So that will give us 0 minus 0 minus 0, which is 0. So the z coordinate at 0, 0 is also 0. So this is a saddle point. Okay, and then we're going to check for the second critical point, which is the second, okay, this one, 9, negative 3. Okay, now we need to check for G. G at point 9, negative 3 will give us negative 24 times y. Y here is negative 3. Minus, minus 36. Okay, so that will give us, hang on, 24 times 3 minus 36 is 36. Okay, so G here is positive. So G positive can be case A or case B. So we have to check for fxx. So fxx at point 93, well, this is our fxx. It doesn't depend on x and y, so it is negative 2. So here fxx is negative, G is positive, so it falls into case A. So here we have a local maximum. Okay, so if you want to know what the value of the local maximum is, you get the value of z when x is 9 and y is negative 3. So we can go back here. Okay, we want to know what happened to z. What is the value of z at 9, negative 3? So replace y with negative 3 and x with 9 minus 9 squared. Okay, get your calculator. So we have 2 times, oh, that would be negative. Minus, so that would be plus again. 9 3 and minus 9 squared, so we get 27. Okay, so the maximum value is here is a 27. Okay, so we have a saddle point at the origin 0, 0, 0, and we have a local maximum when x is 9 and when y is negative 3. Okay, so that's how you find the critical points by solving two equations simultaneously. One is partial f partial x equals 0, and the other is partial f partial y equals 0. And then next step is to find g, where g is fxx times fyy minus fxy squared. And then you test for the value of g at every critical point, and then from there you can get the conclusion. And remember, when g is positive, you have two cases. It can be local maximum or local minimum, so you have to check for fxx. But if g is negative, straight away you can tell it's a saddle point. Okay, that's all. Thank you.